Welcome to another IB Environmental Systems and Societies video. This is a review video as you prepare for your IB ESS exams covering all of topic 1. This is for the syllabus that was originally published in 2017 and with final exams in 2025. Let's get into it. Hi, welcome. Today's video is about the IB Environmental Systems and Societies course subject 1, Foundations of ESS. And here we're going to focus on influences on the modern environmental movement. Right? The big idea here is that historical events and other influences have an impact on the way people perceive and respond to environmental issues around the world. We call that worldview an environmental value system. And the inputs to value systems come from a variety of sources. They can come from literature, other media, major environmental disasters, often which are depicted on the media, such as television, international agreements, and new technological developments. The list I'm going to share with you today is not comprehensive, but it's a really good start. And I've tried to put it in by category. So we'll begin with some things from literature. In the mid-1800s, Henry David Thoreau's Walden introduced this idea of transcendentalism, that nature is divine. And he clearly promoted what we call self-reliant, soft ecologist. That's an ecocentric or an earth-centric environmental value system. Right? Other literature was Aldo Leopold's Sand County Almanac in the mid-20th century, which introduced this idea of human stewardship over natural systems. Probably the most famous example from literature that you can cite on your ESS exams is Rachel Carson's 1962 masterpiece, Silent Spring. It showed the link between pesticide use and ecosystem health, and was kind of the beginning of the end of this pesticide called DDT, which you will encounter elsewhere in the ESS syllabus. Some of my personal favorites from literature are Edward Abbey's books, Desert Solitaire and The Monkey Wrench Gang. That kind of began an era of environmental activism, particularly in the United States in the mid to late 20th century. Media has also played a major role in spurring the modern environmental movement. This began back in the 19th century with John Muir and the foundation of the Sierra Club. They made people aware of the natural beauty of the Yosemite Valley. And that was really the first large-scale environmental preservation society. It expanded on this view of an Earth at the center of a value system, the ecocentric viewpoint. Unfortunately, they actually lost their battle over big dams, and some of the land that they tried to protect was, in fact, inundated. Right? Media plays a big role in people being exposed to natural disasters. A very famous natural disaster that unfolded on television was the Bhopal disaster in India in the mid-1980s, where literally overnight, thousands of people and livestock died from a gas leak. Union Carbide was seen as this big, kind of faceless corporate entity that ultimately paid very little in penalties compared to the human life that was lost. It made people realize kind of the ugly side of industrialization, particularly how they were exploiting poor or impoverished people around the world. Chernobyl in mid-1980s again played out on national television around the world. At the time, it was the worst nuclear disaster in history, and it really brought home this idea that environmental issues are not confined to a single national border, because people watched this cloud of radiation drift across Europe. The Deepwater Horizon explosion in the Gulf of Mexico in 2010 burned for many, many days. It was a record-setting oil spill. And it was updated on live television for hours and hours. And one of the things that came about on that is that it's had a negative impact on the future of offshore oil drilling. So it impacts the value of resources, which we'll touch on in another part of the syllabus as well. Other natural disasters that you'll want to keep in mind for your exam are things like the passenger pigeon extinction in the early 20th century. These pigeons were some of the most abundant on the planet until people ate all of them. And so it changed people's attitudes around what felt like endless resources, and it aroused an overall interest in conservation. The Dust Bowl in North America in the mid-1930s wiped out entire families, forced large-scale migration, and prompted lots of new agricultural techniques that contribute to soil conservation, which we will cover in topic 5 of the syllabus a little bit later on. Some of the other natural disasters that you should be aware of is Minamata. There's a disease named after it. It all resulted from mercury poisoning in the fish that people were eating in Minamata Bay in Japan. Love Canal exposed people to the dangers of toxic waste and their impacts on human health. And it also spawned some grassroots activism. 3 Mile Island was another nuclear meltdown that made a lot of news because it was broadcast on the media. The Fukushima nuclear meltdown in Japan in 2011 continues to get some media attention because they continue to release contaminated water to dilute across the ocean. International agreements, such as the formation of protected areas like Yellowstone National Park, began in the late 19th century. We've got agreements such as CITES, the Convention on the International Trade in Endangered Species, which we will investigate in some detail in topic 3. The Brundtland Report, which actually brought about the idea of sustainable development, which we will touch on later on in topic 1, and the Montreal Protocol, which we will study extensively in topic 6, and is an example you absolutely must have when you go into the exam because it is broadly considered the most successful international agreement on an environmental issue in history. Right? We also had many Earth summits, all the different COP summits that have happened over the years, the Kyoto Accord, the Paris Climate Conference in 2015. All of these events shape the way people perceive environmental issues around the world and respond to them and change their behaviors or not change their behaviors. Those worldviews are called environmental value systems, and these are the influences on them.
Hello, everyone. Today I'm going to talk about systems and models, topic 1.2 in the IBDP Environmental Systems and Societies course. First, let's define what a system is. A system is a set of interrelated parts that work together to form a complex whole. For example, an ecosystem is a system that consists of living and non-living components that interact with each other and exchange matter and energy. This is called a systems approach, which is a way of visualizing a complex set of interactions that may be ecological or societal. A systems approach can help us understand how different factors affect each other and the whole system. Barry Commoner, who was a researcher, famously said in the 1970s that the first rule of ecology is that everything is linked to everything else. I'd like you to remember that idea as you go through this entire course, because when you examine living systems, you always want to look at how one part is connected to another. One of the benefits of using a systems approach is that it can reveal the emergent properties of the system. Emergent properties are characteristics or behaviors that arise from the interactions of the parts, but are not found in any of the individual parts. For example, the emergent property of an ecosystem is its biodiversity, which is the variety of life forms and their interactions within the system. Biodiversity is not a property of any single organism, but of the whole ecosystem. The concept of a system can be applied to a range of scales, from microscopic to global. For example, at the microscopic scale, we can study the system of a cell, which consists of organelles, molecules, and atoms. At the global scale, we can study the system of the Earth, which consists of different spheres, such as the atmosphere, the hydrosphere, lithosphere, and biosphere. A system is comprised of storages and flows. Storages are placed where matter or energy is accumulated or stored within the system. Flows are movements or transfer of matter or energy into or out of the system. The flows provide inputs and outputs of energy and matter for the system. The flows may be classified as transfers, which is simply the movement from point A to point B, or transformations, which is a change of form or state. For example, water moving from one place to another through precipitation, runoff, or infiltration is a transfer because it's simply the movement. A transformation is a change in the chemical nature, state, or energy level of matter or energy. For example, photosynthesis transforming light energy into chemical energy stored in glucose molecules is a transformation. In systems diagrams, storages are usually represented as rectangular boxes and flows as arrows, with the direction of each arrow indicating the direction of each flow. The size of the boxes and the arrows may be representative of the sizes of the storages or the flows. A system can also be classified as open or closed or isolated. An open system exchanges both energy and matter across its boundary with its environment. For example, an ecosystem is an open system because it receives inputs of solar energy and nutrients from outside and releases outputs of heat and waste materials to the outside. A closed system exchanges only energy across its boundaries with its environment, but not matter. For example, a terrarium is a closed system because it receives inputs of light energy from outside, but does not exchange any matter with outside. An isolated system is a hypothetical concept in which neither energy nor matter is exchanged across its boundary with its environment. For example, an ideal thermal flask is an isolated system because it does not receive or release any energy or matter from or to the outside. However, isolated systems do not exist in nature. They only exist in extremely tightly controlled laboratory environments. Ecosystems are open systems because they exchange both energy and matter with their surroundings. Closed systems exist experimentally, such as in laboratories or controlled experiments where matter exchange is prevented or minimized. However, closed systems do not exist naturally on Earth because there is always some degree of matter exchange between different parts of the Earth system. The global geochemical cycles approximate to closed systems because they involve large-scale movements and transformations of matter within the Earth system without significant loss or gain from outside. A model is a simplified version of reality and can be used to understand how a system works and to predict how it will respond to change. A model can be physical, such as a scale model of a building or a globe, mathematical, such as an equation or a graph, conceptual, such as a diagram or a flowchart, or computer-based, such as a simulation or an animation. A model inevitably involves some approximation and therefore loss of accuracy because it cannot capture all the details and complexities of reality. Therefore, models need to be evaluated for their validity, their reliability, their accuracy, and their usefulness for different purposes and situations. To construct a model from a given set of information, we need to identify the key components and processes of the system we want to model and decide how to represent them using symbols and rules. We also need to make assumptions and simplifications to reduce the complexity of the system and to focus on the most relevant aspects. We then need to test and refine our model using data and observations to check if it matches reality and to improve its accuracy and reliability. To evaluate the use of models as a tool in a given situation, we need to consider the advantages and disadvantages of models for that purpose. For example, climate change predictions are based on computer models that simulate the interactions of different factors that affect the Earth's climate, such as greenhouse gases, solar radiation, clouds, oceans, land use, and human activities. These models are useful because they can help us understand the causes and effects of climate change and explore different scenarios and outcomes under different assumptions and policies. However, these models also have limitations because they're based on incomplete or uncertain data, and they may not account for all the feedbacks and uncertainties that influence the climate system. Therefore, these models need to be constantly updated and validated with new data and observations, and they should not be taken as absolute truths or as certainties. Models in general are simpler to understand. You can change them without disastrous effects because you're not actually changing the real world or natural systems. And you can use them to predict hypothetical scenarios, what might happen if, etc., etc. Disadvantages of models, of course, are that they are incomplete. We don't know if their results are entirely accurate because they are only as accurate as the data that humans have put into them. That means they're also liable to human error. In conclusion, systems and models are essential tools for studying environmental systems and societies. They help us describe, explain, predict, and manage complex phenomena that involve multiple factors and interactions. However, we also need to be aware of their limitations and uncertainties and use them with caution and critical thinking. Thank you for your attention. I hope you have learned a bit more about IBESS Topic 1.2, Systems and Models. This is a fundamental set of ideas that you will encounter throughout the ESS course.
Hello, everyone. In today's video, we're going to address topic 1.3, Energy and Equilibria in the IB Environmental Systems in Societies syllabus. I'm going to talk about thermodynamics, equilibrium, feedback, resilience, and tipping points, which are all important concepts in environmental systems and societies. One of the big ideas in this topic is that the laws of thermodynamics govern how energy flows through ecosystems and dictate its organisms' ability to do work. First, let's review the laws of thermodynamics, which are the fundamental principles that govern the behavior of energy in ecosystems. The first law of thermodynamics is the principle of the conservation of energy, which states that energy in an isolated system can be transformed, but it cannot be created or destroyed. You've probably encountered this in a chemistry lesson at some point. This means that the total amount of energy in a system remains constant, although it may change from one form to another. For example, in a food chain, the chemical energy stored in organic matter is transformed into kinetic energy, or movement, heat energy, or thermal energy, and other forms of energy by different organisms, but the total amount of energy does not change. The first law of thermodynamics allows life to exist on Earth because it implies that energy can be transferred from one system to another. For example, the Earth receives solar energy from the sun, which is the main source of energy for most living organisms. Without this input of energy from the outside, life on Earth would not be possible. The second law of thermodynamics states that the entropy of a system increases over time. Entropy is a measure of the amount of disorder or randomness in a system. An increase in entropy or disorder arising from the energy transformations reduces the amount of energy available to do work. This means that every time energy is transformed from one form to another, some of it is lost as heat or other forms of low-quality energy that cannot be used by living organisms. For example, in a food chain, only about 10% of the energy available at one trophic level is transferred to the next trophic level, while the rest is lost as heat or waste. This 10% rule is responsible for the structure of ecological pyramids, in which the top trophic levels contain less biomass than lower levels, and is why there are fewer organisms at higher trophic levels. The next significant idea in topic 1.3 is that an equilibrium is a state where there is no net change in a system over time. There are two types of equilibrium, static or dynamic. A static equilibrium is a state where there's no movement or change in a system at all. For example, a rock resting on the ground is in static equilibrium because there are no forces acting on it. It's not going anywhere. Nothing is changing about it. A dynamic equilibrium, on the other hand, is a state where there is movement or changes in a system, but it's balanced by opposing forces or processes. For example, a pendulum swinging back and forth is a dynamic equilibrium because the gravitational force pulling it down is balanced or offset by the tension force holding the pendulum up. As an open system, an ecosystem normally exists in a dynamic or changing equilibrium, either in a steady state equilibrium or in one developing over time, such as in succession, which is what you see on this slide here. This dynamic equilibrium is maintained by stabilizing negative feedback loops, which we'll address in just a couple of minutes. A steady state equilibrium is a state where there are constant conditions and flows in a system over time. For example, a mature forest ecosystem is in a steady state equilibrium because there are stable populations and nutrient cycles within it. A succession equilibrium is a state where there are changing conditions and flows in a system over time until it reaches a climax community. A negative feedback loop is a process that tends to reverse the direction of the initial change and counteracts deviation from an equilibrium. The thermostat regulating indoor air temperature is a good example of a man-made negative feedback mechanism. When the air becomes too warm, the thermostat turns off the heat, causing a gradual drop in the temperature. When the temperature becomes too cool, the thermostat turns on the heat again, raising the temperature. This cycle repeats itself, maintaining a dynamic equilibrium around the desired temperature. Natural systems depend on negative feedback mechanisms for stability. For example, if the population of rabbits increases in an ecosystem, this will increase the predation pressure by foxes, which will reduce the population of rabbits back to its original level. This is a negative feedback loop that stabilizes the population size of the rabbits and maintains the equilibrium. A positive feedback loop is a process that tends to amplify the initial change and drive the system toward a tipping point where a new equilibrium is adopted. You can think of this as the snowball effect. As a small snowball rolls downhill, it picks up more snow, which makes it roll farther and faster, picking up more snow as it goes and growing larger and larger as it rolls. A classic example of positive feedback in natural systems is ice melt driven by climate change. If the temperature of the Earth increases due to global warming, this causes more Arctic ice to melt, which reduces the albedo or reflectivity of Earth's surface, so that Earth's surface then absorbs more solar radiation, and that increases the temperature further. This is a positive feedback loop that destabilizes the climate system and pushes it towards a tipping point. A tipping point is a critical threshold where a small change can have large and irreversible effects on a system. For example, if the temperature of the Earth rises above a certain level, this may trigger a runaway greenhouse effect that could make the Earth uninhabitable for most life forms. The permafrost time bomb is a classic example of this happening. This is a destabilizing positive feedback in Earth's climate system. Warmer temperatures will melt some of the permafrost, which leads to an increase in methane released into the atmosphere by decomposers. Because methane is a powerful greenhouse gas, it drives more warming, which then melts more permafrost, which releases more methane to drive more warming to melt more permafrost. Earth's climate systems contain many overlapping and interdependent feedback mechanisms, which is why climate science is so complex and why predictions about the future can vary so much. The resilience of a system refers to its tendency to avoid such tipping points and maintain stability. Resilience depends on several factors, such as diversity and the size of storages within the system. Diversity, of course, refers to the variety of components and processes within a system that provide redundancy and flexibility to cope with change. For example, an ecosystem with high biodiversity has more species that can perform different functions and roles, which can increase its resilience to disturbances. If one organism dies out or the populations decrease, other organisms are present to fill in that role. Note the number of alternative energy pathways in this food web representing Tanzania's famed Serengeti National Park. Each one of these lines represents a feeding relationship. And if you look at the herbivores here, you'll note that many of them feed on different groups of producers. That level of redundancy diminishes as we move up the trophic levels from producers to primary consumers to tertiary consumers and apex predators. The size of storages refers to the amount of matter or energy that's accumulated or stored within a system, and that can buffer against fluctuations. For example, an ecosystem with large storages of carbon or water has more capacity to regulate its climate and the hydrological cycle, which can increase its resilience to droughts and floods. Humans can affect the resilience of systems through reducing these storages and the diversity. For example, human activities such as deforestation, overfishing, pollution, and urbanization can reduce the biodiversity of an ecosystem, as well as the storages of biomass or water. That then makes those systems more vulnerable to disturbances and moving towards tipping points or new equilibrium. The delays involved in feedback loops make it difficult to predict tipping points and add to the complexity of modeling systems. For example, the effect of greenhouse gas emissions on the climate system may not be apparent for decades or even centuries due to the inertia and lag time of the atmosphere and oceans. Right? We're looking at turnover times of thousands of years and sometimes millions of years in these systems, which is why there are significant time lags. Right? Those time lags make it challenging to forecast the future impacts of climate change and to take appropriate actions to mitigate or offset them or adapt to the changing climate. In conclusion, thermodynamics, equilibrium, feedback, resilience, and tipping points are essential concepts to master when studying environmental systems and societies. You'll encounter these concepts in all of the other topics that we're going to study. They help us understand how energy flows and transforms in systems, how systems respond to change and disturbance, and how humans can influence the stability and sustainability of systems. These next few slides will show some aspects of energy and equilibria that you should be able to apply in an ESS examination situation. You should be able to explain the implications of the laws of thermodynamics to ecological systems. This is something that comes up almost every year in ESS exams. You should be able to discuss the resilience in a variety of systems. You might be asked to compare the resilience of two different food webs, one of them being fairly simple, one of them being fairly complex, and identify that the complex one is more stable and more resilient. You may be asked to evaluate the consequences of different tipping points, right? And you may be provided with a graph or a diagram showing the various interactions and flows of energy and matter within a system. And based on that graphic, tasked to identify how a change in one part will change another part. If you found this tutorial helpful, please give it a like and consider subscribing to my channel. You can find more ESS information and resources at my website, www.mrcreamerscience.com, or by following me on the platforms X and Instagram. Thanks for your time. Happy learning. Hi, good morning. Welcome to my video about IBDP, Environmental Systems and Societies, topic 1.4, Sustainability. We're going to go over the first significant idea of the topic today, and that is that all systems can be viewed through the lens of sustainability. This graphic right here is a little bit misleading because it shows a linear progression from plants growing and making sugars back to plants growing and making sugars at this end, when in fact, this really should be a circular graphic to reflect the circular economy or the circular ideal of sustainability. Right? When we're talking about sustainability, what we're really into is the idea of natural resources. You probably studied natural resources at some point in primary school, but just to recap very quickly, natural resources are materials and services that people use for one purpose or another, and we generally categorize them as either renewable, because they can be replaced or restocked, or non-renewable because they're finite, and you see some examples of each of those here on the screen. In ESS, we also have, we discussed kind of a middle category that I call replenishable resources, and these are resources that can be replenished as long as they're managed appropriately, but their rate of replacement or restocking is slow enough to make it challenging or difficult for people to actually replace them adequately. It's kind of hidden right here behind my picture, but soils are a classic example of a replenishable resource. We can build up soils through soil management techniques that we'll investigate in topic 5, but more frequently, people use up the nutrients and degrade soils more quickly than we're growing new soils or developing soils in places where they didn't used to exist. Similarly, with potable water, particularly groundwater, we can replenish it, we can replace it, but it's a slow process, and people don't generally do it quickly enough or manage their consumption to be slow enough to allow that replacement. One of the key terms that you've got to take away from topic 1.4 is this idea of natural capital. Right? This is how much we have, a storage of a natural resource. Right? So how much fresh water do we have? How many soil nutrients do we have in a particular area? Right? What's the total cubic feet of minerals or wood in a particular area? Right? They are generally things that people value either monetarily, they can put money, or they can put a dollar amount on them, or they value them intrinsically. Natural capital can also come in the form of services that ecosystems provide for us. The clearest example of an ecological service is that all of our trees and plants and algae and cyanobacteria on Earth produce oxygen from photosynthesis. That oxygen production, we can't really put a dollar value on it, because it's a requirement for most forms of life. Right? Carbon sequestration, it's a great service. It's extremely valuable because it helps regulate the greenhouse effect in our atmosphere. These are things that our natural environment does, not only for people, but also for all of the other organisms living in those systems. Natural income, we're going to come up, natural capital, right? This is the standing stock. What we have is the storage of either those goods or those services. Natural income is how those goods or services grow or increase. It's like the growth of money in a bank account. It's like the interest on your savings, right? So it's how much the natural capital increases over a fixed period of time, usually 1 year at a time. So the idea with natural capital and natural income is that for something to be sustainable, for a practice to be sustainable, we don't want to diminish the storage, the natural capital, right? As the natural capital grows or increases, right, it's going to produce natural income. That is the growth, the increase over the original amount. Then from that natural income, we can harvest that. And as long as we don't harvest more than what was grown or what was replaced by the natural capital, so that what we started with remains constant, then it's sustainable. Right? If we have a woodlot that produces or that grows approximately 1,000 board feet of new timber every year, we can harvest up to 1,000 board feet of timber every year and still maintain our woodlot or our forest. But if we harvest anything more than 1,000 cubic feet a year, maybe even as little as 1,100 board feet, then slowly we're going to chip away at what we started with, and that means that our resource consumption is unsustainable. It's no longer working. Because we're no longer preserving what we started with, right? So here you have a nice little range of items, and some of these are ecological goods, and some of these are ecological services, right? So soil formation, photosynthesis, right? Those are examples of ecological services, right? Pollination is a service. Flood control is a service. Purifying water is an ecological service. Storing carbon or carbon sequestration, that's an ecological service. Right? Some of the things that might be ecological goods are, of course, the food, what we can get for both ourselves or for other organisms living in the ecosystem. That is an ecological good. Clean water is a good produced by the service of water purification. Wood is a good, and growing the wood is an ecological service that produces another good, like the habitat. So this might be a 4-mark question that you would encounter on an IB ESS exam. Explain the relationship between natural capital, natural income, and sustainability. So in your response, you need to have all 3 of those underlined words. And because this is explain, you need to tell how they are related and why they are connected. So natural capital is the standing stock or the beginning amount of a natural resource that we have. And as it grows or increases, that growth or that increase is called natural income. And that natural income can either be goods or services. If we use those goods or services at a rate that is less than the growth here, so that the total amount of the natural capital or the standing stock that we had remains constant or increases, that is a sustainable practice. If, however, we extract goods or degrade the services in a way that we consume them at a rate greater than the capital grows or increases, so that we chip away at the amount of natural capital we began with, that's an unsustainable practice, because eventually that amount of natural capital is going to get smaller and smaller until it disappears entirely. I hope you found this helpful. If you did, give it a like, consider subscribing to my channel. Thank you. Here we're going to recap the second big idea of ESS topic 1.4, sustainability. And that significant idea that you see right here on the screen is that sustainable development means meeting the needs of the present without compromising or reducing the ability of future generations to meet their own needs. We're looking at sustainable use of natural resources. This is where natural capital and natural income come into play. Great. Your first understanding statement from the syllabus is this big long thing here. Factors such as biodiversity, pollution, population, or climate can be used quantitatively as environmental indicators of sustainability. These factors can be applied at a range of scales, from local to global, Millennium ecosystem assessment, blah, 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 blah. It's way too much information to remember as written. So let's break it down into smaller bits and look at it piece by piece. All right. First, biodiversity, pollution, population, or climate can be measured. We can get quantitative numbers from them and use those to indicate sustainability. That's why they're called environmental indicators. And there's a bunch of different ways to measure or assess those indicators. Right? Biodiversity. We previously looked at how biodiversity, the more diversity we have, the stronger an ecosystem is, the more resilient it is to change. So greater diversity means greater ecosystem stability, which means it's more sustainable. Well, how do we measure biodiversity? We'll get into that when we get to ESS Topic 2.5 in a few weeks. Right? There's a tool called Simpson's Diversity Index. It's a mathematical model that you can apply from your field measurements, and I'll teach you how to do that. Pollution. This is something that humans put into the environment that has an adverse or negative impact on the environment, generally affecting the abiotic factors, which then subsequently influence the biotic factors of the environment. Right? So the less pollution there is, the lower the impact there is on living organisms. Therefore, that's more sustainable. Our next topic in the syllabus is called humans and pollution. So we're going to look at some of the ways to measure pollution in that topic. We'll also touch on it in the subtopic dedicated to water pollution in topic 4 that will come up later this year. Populations, right? Similar to Simpson's Diversity Index, right? We can measure populations. But in this case, we're looking at initially human populations, right? The more people there are on the planet, the more resources we typically consume. So more people means more pressure, which means that's less sustainable. Since we're talking about assessing the environment, if we look at plant or animal populations or populations of other organisms that are not people, generally speaking, the more stable an ecosystem is, right, the greater the populations are, the greater diversity you have within those populations due to genetics, that means the ecosystems are more stable and you have a more sustainable approach. And we're going to look at some tools about both of those. Ecological footprint is going to come up in just a few minutes, and then we're going to revisit it at the end of the course when we go into topic 8.4 about humans and resource use. Right? Climate might be challenging for us in a high school setting to measure or assess directly, right? But there's a lot of data that professional scientists are gathering that we can use to assess sustainability of different human actions. Right? The number one indicator there are levels of greenhouse gases in the atmosphere. Right? If we have stable levels of greenhouse gases, the greenhouse effect that provides for life on our planet remains stable. It doesn't lead to a runaway positive feedback mechanism called climate change, right? Stable greenhouse gases create stable global temperatures. That's a more sustainable approach. Right? As we change the greenhouse gases, that changes the environment, and it's the environment that determines which organisms survive. So we'll revisit that concept from evolution when we get into topic 3 about the origins of biodiversity and how the environment applies that selective pressure to determine who lives and who dies. Right? All of those environmental indicators, right? Biodiversity, pollution, populations, and climate, we can apply those on a global scale. We can also apply them on a very narrow basis at a local scale. Right? Understanding statement number 5 is that the Millennium Ecosystem Assessment, or MA for short, right, gave a scientific appraisal or a measurement of trends in the world's ecosystems and the services that those ecosystems provide to people. Right? So the purpose of it really was to figure out how people are impacting the planet. The major takeaways here, I've written them in red. More diversity loss in the past 50 years than at any other time in human history. We may have increased the wealth and health of human populations, but doing so has come at the expense of the ecological goods and services that we discussed previously in topic 1.4 about natural capital and natural income. Right? That natural capital is being harvested unsustainably. Right? We're taking more than the income every year. So we're drawing down on that account, that standing stock of natural capital every year. Right? And remember, the first law of ecology is that everything is connected to everything else. So if we are taking down or drawing down our stock of natural capital in the environment, that's ultimately going to lead to harm to human populations. This is environmental systems and societies. Our societies are a part of and interdependent with environmental systems. Sustainable solutions are possible to all of these issues, but they do require international coordination and collaboration, which is quite challenging. The next big idea in topic 1.4 is that environmental impact assessments are important for sustainable development. Let's look at the name of this thing. It's an assessment, means to measure. So we want to measure the environmental impact of our actions. Right? That's what an EIA does. It's how do we measure the environmental impacts of what we're doing. Right? EIAs are going to be different depending on the size of the project, depending on which country it takes place, but they all follow a fairly basic or a fairly similar structure. Right? First, you want to go a baseline study, right, to figure out the current state of the environment before the project begins. Right? And we're looking at environmental impacts, we're looking at social impacts, we're looking at economic impacts. So we measure the current state of things. Then we start planning. If we want to go ahead with a project like a dam or a major road or some other type of big infrastructure project, right, we know that it's going to have environmental impacts. We know that it's going to have social impacts. We know that it's going to have economic impacts. Well, how do we reduce the environmental impacts? How do we make it so that the social impacts or the economic impacts are beneficial to a majority of the people? Then, assuming we've come up with a good plan, we implement the plan, say, here's how this is the plan that's been approved. Let's follow along with it. Let's continue to measure it and monitor how that's happening. And then the final stage over here says assess, and that's monitoring and evaluation, right? Were the impacts that we predicted back here actually as we predicted that they would be? Do we need to change the project as a result of impacts not being what we predicted? Right? An EIA is a tool that decision makers like governments and big developers can use to determine the scope of the impact of one of their projects. In some places, it's not a government requirement. In many places, it is. And frequently, because governments generally represent people and other organisms have less of a voice in government or big business decisions, the socioeconomic factors generally will prevail over many of the environmental factors. That's not always the case. That is a generalization, but that is frequently true. One of the things you're going to need to do in this topic is evaluate EIAs. So here's one step to that, or here's one part of that. Right? Criticisms of EIAs is that there is no such thing as a standard practice for an environmental impact assessment. An environmental impact assessment for a dam project in Cambodia is going to be very different from an environmental impact assessment for a uranium mine in Tanzania, which will be very different from a proposed shrimp or prawn farm in Vietnam. It's also quite difficult to define the system boundaries. Again, back to this idea that everything is connected to everything else. If everything is connected to everything else, an impact on one part of the system is bound to have knock-on effects in the connected parts of the system. So those could be considered indirect impacts. And how do we assess those? We know they exist, but to what extent and how far out do we continue to measure them or assess them? Here's another tool that decision makers can use to guide their planning process as part of an environmental impact assessment. It's called an ecological footprint. All right. This is an area of land and water that is theoretically required to provide everything that we need to stay alive sustainably. That means indefinitely, right? If the ecological footprint is greater than the area available to a particular population, then that means the population, their habits of resource use and consumption are not sustainable, right? Ecological footprint is a theoretical model. It's not an actual measurement of the amount of land that's dedicated to farming and the amount of land that is built up into cities and roads. It is not a measure of the volume of water that is consumed for human use and agricultural irrigation. It's a model, right? And it's a model that's a function of the habits and resource consumption of a person, or more broadly, of populations, right? Again, it's a theoretical model. It's how much stuff we use, how many resources we use in order to stay alive for a year. This is going to come back to the idea of renewable and non-renewable resources. We need to give those resources time to renew themselves for new fish, new animals to be born and to mature. We need to give the environment time to absorb our pollutants, our greenhouse gases, the carbon that we're emitting. We need time for those forests to grow and pull that carbon out of the atmosphere. We need time to allow nutrients to be replenished in the soil. Right? So the ecological footprint comes back to not only the idea of sustainability, but this idea of renewable versus non-renewable natural capital. We've seen this relationship between natural capital, natural income, and sustainability already. Right? We're looking at what are these values, what's the value of ecosystem services to society? We've just looked at we need time to allow things to happen, such as carbon sequestration or fish populations to restock or to regrow. Right? How much would you pay for those ecological services? How much is oxygen worth to you? Can you put a dollar value on that? All right. You may be tasked to evaluate or discuss how environmental indicators, such as that Millennium assessment, can be used to measure the progress of a project or to measure how sustainably something is happening. Right? If you're going to evaluate something, you're going to have to weigh the pros, weigh the cons. And if you're going to look at the progress of a project, you need to know where it started. That's your baseline study. You need to know where things are during and after the project. That's your environmental monitoring. You need to know what to measure. Those are your environmental indicators. And you need to know how to measure them. We'll get into some of those when we get into topic 2.5, investigating ecosystems, in just a little while. You'll also be asked to evaluate the use of EIAs, and they won't ask you to evaluate a particular environmental impact assessment. You might be tasked with evaluating the concept of an environmental impact assessment more holistically. Right? What are the strengths of it? Allows us to assess sustainability. What are the limitations? Well, it's not carried out the same way everywhere in the world. One of the limitations may be that even though we've identified that a project will have negative environmental consequences, the social and economic benefits of that project may be determined to outweigh or outstrip the environmental concerns. And so the project goes ahead anyway. I mean, you should be able to look at both sides of that argument. All right? Explain the relationship between ecological footprints and sustainability. I just want to come back and remind you, the ecological footprint is a model. It's a theoretical tool to assess sustainability. We're looking at how much do we need to stay alive year after year based on our resource use habits. Okay? International mindedness, right? Your environmental impact assessments, they're different depending on where they are, right? We have all these COP summits that are happening. The intention is to develop tools and treaties and agreements to help monitor and assess human impacts on the environment. So these international conferences are kind of like giant environmental impact assessments, right? And they incorporate a lot of baseline knowledge from a wide range of fields, right? I hope you enjoyed this video. If you did, give it a like, consider subscribing to my channel, and share it with other people. Thanks. Hi, welcome back to another video about IBDP, environmental systems and societies. Today's video is about topic 1.5, humans and pollution. The first big idea from this topic is that pollution is by definition a human disturbance in the environment. You can see from this photo from where I used to live in Tanzania, this nice beach environment has clearly been disturbed by humans. I don't think anybody would argue that this is not a form of pollution. When we get into more depth into the definition of pollution, there's really four big elements to it. The first is that it's made or caused by people. The second is that we're adding something to the ecosystem. The third is that we add it to the ecosystem faster than the ecosystem can process it. And fourth, that once we have added it to the ecosystem, it has some type of impact on life there. So to recap, the four parts of the definition of pollution is that it's something that is made or caused by people, that we've added to the environment faster than the environment can process it, and which has an appreciable impact or effect on the living organisms in that environment. There's a bunch of different types of pollutants, and for your ESS exam, you should be able to discuss and give some examples of each of these types, at least broadly. Right? So first, we have organic or inorganic substances. Organic meaning carbon-based. So you may have things like sewage or animal waste, because those are nutrient rich and they come from living organisms. But a lot of organic pollutants are also long, complex carbon-based chains or big molecules built around organic carbon structures, particularly older pesticides, which we call persistent organic pollutants. And I'll get into those in a minute. We also have inorganic pollutants. And pollution may also take the form of excess energy in the ecosystem. That can be light pollution, as you see in this image, where over here on the left is what the night sky looks like inside a city, and over here on the right side is what it looks like in the middle of the ocean or deep in the African savanna, where you're far from large human settlements. Right? People may also have excess sound in the environment. We've seen this in urban landscapes where the noise of traffic overwhelms the sounds that animals, particularly birds, use to communicate, and it interferes with their ability to share information about predators or to find mates. We also may add excess heat, generally in the form of hot water, to aquatic environments, and that will change the temperature range for the organisms that live there and may push them beyond where they're comfortable or capable of surviving regularly. Another pollutant, and a lot of people don't think of this as a pollutant, but it is when humans bring in invasive species. We may not have made the invasive species, but it's something that humans have done, and we've added that to the environment. So this plant you see here is called kudzu, and it's pretty famous where I grew up in the United States. It's called the plant that ate the South. It was originally brought in for the good purpose of erosion control on road projects, but because it had evolved in Asia and not North America, there were no natural predators or herbivores in North America that ate this plant. So it just grows unchecked. And you can see here it grows and covers entire hillsides. These are all trees that it's grown across, and that it's covered, and it will kill those trees because they can't photosynthesize since they no longer have access to sunlight. And of course, one of the big pollutants that I think most people are aware of these days are the combustion of fossil fuels and the release of carbon dioxide and other greenhouse gases into our atmosphere, thus impacting the entire planet's climate. Right? Pollution sources may be classified as either point source or non-point source. And I want to address the point source pollutants first, because that's the easiest one to kind of wrap your head around. Point source, right, is where the source of the pollutant comes from a single point. Right? This image kind of exemplifies that. It's a single pipeline going in, or it's a single factory that's emitting emissions into the atmosphere. It's pretty easy to identify where it comes from. Non-point source pollution is actually pollution where it's like a little bit of pollution from a variety of sources all cumulatively adds up to an excessive level of input into the environment that has an impact on the organisms that live there. A classic example of that is agricultural runoff. The runoff from one individual farm may be relatively small, but over the entire landscape, you have many farms, each of which contribute a small amount of pollution. Collectively, it becomes a significant impact on the environment. Right? The point source pollutants, again, usually a single source where you can find it on a map. Its regulation or control is relatively simpler because you can point directly to the source. This particular storage facility has a bunch of leaking barrels in it. It's pretty easy to go in and fix that problem because you know exactly where the leak is coming from. Right? Non-point source pollution is much more challenging to deal with because it's coming from so many different sources. The sources might not all be within the same political boundary, and so they may be in different jurisdictions, which means it's difficult. Not only is it difficult to identify who's in control, it's difficult to identify who is responsible for the release of the pollutant. Right? It generally requires large-scale interventions, which means getting a lot of people to change their habits. That's a tier 1 strategy, and while that's the most effective, it is also generally the hardest to accomplish. The next type of pollutant we're going to cover are the differences between persistent pollutants and biodegradable. Right? Persistent means they persist, they last a long time, they do not degrade. Right? And persistent pollutants lead to two different processes, one called bioaccumulation and one called biomagnification, which I'll explain in a little bit more detail later on. Biodegradable pollutants, as you might guess by the name, can be degraded or broken down through living processes. These are generally your organic pollutants. They may be more modern pesticides that are not persistent, right? So your persistent pollutants, things like your persistent organic pollutants, things like DDT, heavy metals such as mercury or arsenic, right? The bodies of consumers cannot degrade or break down those pollutants. That's why they're persistent. And because they are persistent and they're not broken down and the body doesn't excrete them, right, they tend to build up in each individual organism's body. So when they build up, they accumulate over time in the organism's biomass. That's what we call bioaccumulation. So bioaccumulation is the slow buildup of pollutants within a single organism's body as it consumes the pollutant over time. What happens as a result of bioaccumulation is that the concentration of the pollutant within each trophic level in an ecosystem tends to increase, because if you have a pollutant in the water or in the sediment in an area, right, the producers that grow there will absorb a little bit of that pollutant. And every time your primary consumers eat some of those producers, they absorb and retain that pollutant. Then each time the secondary consumers eat some of the primary consumers, they also absorb and retain that level of pollutant. But because the primary consumers had more of the pollutant in them than the producers did, the concentration in the consumers is higher than it is in the producers. So each time you jump up a trophic level, the concentration of the pollutant also increases. And if you see the numbers in this diagram, they may increase by a factor of 10. And what that means is that by the time you reach the higher trophic levels, right, your apex predators or your tertiary consumers, you have high concentrations of persistent pollutants in their bodies. Right? So there's two processes here: bioaccumulation within an individual organism's biomass over its lifetime, and the biomagnification, or increasing concentration of a pollutant in trophic levels following the matter flow in a food chain. Right? So some good examples there of your persistent pollutants, again, are DDT. We're going to come back to DDT because it is an important example. Right? Pollutants can be classified as acute or chronic. Acute is very short term. Right? This may be where there's a single accident. Maybe there's a chlorine leak from a swimming pool, or there's a train derailment, and whatever the train is carrying is some type of a chemical that's released as a result of the accident into the atmosphere. That's a short-term, acute instance of pollution. Frequently, that's a point source pollution, but not always. Right? Chronic pollution is long-term, and generally it's kind of a long-term, low-level exposure. So you may not notice it, but it does create notable impacts on living organisms over time. Probably the most prominent example of chronic pollution is urban air pollution. It causes all types of respiratory illnesses and cardiovascular diseases in urban human populations, because a single day of urban air pollution may not have long-term effects, but many years of living and breathing that air pollution will have long-term effects. Okay? Pollutants can be broken down into two categories, either primary or secondary. We'll get into these in much more detail when we get to topic 6 about atmospheric systems and societies. But primary pollutants are the ones that upon their release from their source, are active and have a negative impact on living organisms. That's different from secondary pollutants. Secondary pollutants are the result of chemical change or chemical reactions, either in water systems or in the atmosphere or in the soils. And the secondary pollutants are the ones that actually cause the impact on living organisms. Right? You don't need to know these figures. Right? You don't need to know the numbers. But if you'll notice here, right, a carbon monoxide is a common primary pollutant resulting from transportation. Nitrogen oxides come from stationary source fuel combustion. Those are things like your power plants that produce electricity. Okay? Your particulates may come from transportation. They may come from industrial processes, right? But these sulfur oxides, right, you come from solid waste disposal here. They may also come from your energy power plants, right? So being able to identify some specific pollutants and where they may come from will be useful examples to have on your ESS exam. The secondary pollutants here, your classic example is photochemical smog. Again, we'll revisit this when we get to topic 6, the atmosphere. All right. So the initial pollutant that is released is the nitrogen dioxide, which comes frequently from automotive exhaust. Right. The NO2 is not itself the thing that causes harm to human or other organisms, but what it does is it reacts with water in the atmosphere to form nitric acids and aldehydes, and those create the photochemical smog, and the smog itself is what has the impact on human health and environmental health. Right. Pollution management strategies. This is probably one of the most important concepts in the environmental systems and societies course. So make sure that you know this part really well. Right. Regardless of what the pollutant is, the strategies that people have for dealing with it can be broken down into one of 3 tiers. And you might want to think of these as most effective to least effective. Tier 1 is where we change the human behavior. In other words, we stop producing the pollutant entirely. And we do that by changing the way we do things. It may be replacing fossil fuels with renewable energy sources. It may mean replacing gas-blown plastics with some other way of protecting our items when we ship. But what it means is we actually stop producing the pollution in the first place. So we've actually stopped it at its source. We've dealt with the source of the pollution, right? That's why it's the most effective, because you stop it where it starts. The second tier is simply where we're still producing some of the pollution. We're just producing less of it, right? So we do this by increasing the gas mileage or the fuel mileage on vehicles. So a car that can go farther on a liter of fuel will release fewer grams or kilos of carbon dioxide into the atmosphere because it is burning less of the fossil fuels. Right? It's still releasing CO2 into the atmosphere. It's just releasing less of it. Right? The third tier is where we have to go in and clean up damaged ecosystems. This is the least effective because we're still releasing the pollutant into the ecosystem. We're just going in and cleaning up afterwards. So we clean up, and then because we're still releasing the pollutant, we have to go in and clean up again. We release the pollutant and we clean up again. So it's kind of a never-ending cycle, which is why it's the least effective. It also tends to be very expensive. Okay, let's talk about DDT, because it's one of those classic examples that shows up almost every year on the ESS exams in some way, shape, or form. And what you need to be able to do with DDT is evaluate its use. Why was it used? Why was it helpful? What are the pros? What are the negative impacts of DDT? And then make an argument or a conclusion based on an environmental value system about whether the pros outweigh the cons or vice versa. right? You would definitely not need to know this big long word here, dichloro-diphentrichloroethane. Just write DDT. That's all you need to know, right? So it was first introduced because it's a great pesticide. It kills mosquitoes, and mosquitoes are pathogen vectors. They carry malaria, dengue, yellow fever, a bunch of other tropical diseases that make people really sick and contribute to early human deaths, right? Once we figured that out in the mid-20th century, that it was really useful for controlling those insects, it became adapted and used in agriculture to kill agricultural pests, many of whom are also insects, right? Then, once we realized, kind of thanks to Rachel Carson's Silent Spring, published in 1962, that DDT had some pretty significant negative impacts on the environment and on human health, we stopped using DDT. All right. Not only did it kill the mosquitoes, right, but it also had significant and broader impacts on the environment. So here you can see in this map, this is where the species of mosquito that's responsible for spreading malaria existed in South America and parts of Central and North America as well in the 1930s. Then DDT was widely used and essentially wiped out those mosquitoes, except for in a few countries that were still using it. And then after the DDT ban went into place and people stopped using it, they replaced it with something else, right? Those mosquitoes moved back in and reclaimed their previous territory, which means the incidence of those diseases also rose in those areas. Okay, so its effect on the environment. We know that DDT thins out the shells of bird eggs and results in higher mortality rates among bird species, and that then has an impact on the environment because it disrupts food chains. We also know that DDT is a persistent organic pollutant, so it bioaccumulates in different organisms, and then it biomagnifies up the food chain. And so because it is persistent and it has these detrimental health impacts on your top trophic levels. In addition to that, we know that it has all of these negative impacts on human health. So you may be asked to construct a systems diagram to show impact of a particular pollutant when that happens on an exam. When that happens on an exam, you'll probably be given a specific example and asked to comment on it. I can almost assure you that on the ESS exam, you will be asked to evaluate the effectiveness of these 3 tiers of pollution management with reference to a specific pollutant. It won't just be broad where they ask you to describe or explain each of these tiers. They'll ask you to apply it to a particular pollutant and evaluate the effectiveness of each level. Okay? And then you'll probably also encounter some kind of a question about DDT. And it generally falls into this kind of format somehow. State 1 pro and 1 con, or 1 advantage and 1 disadvantage of the use of DDT, and then evaluate its use, or describe its impact on human health, describe its impact on natural ecosystems. All right? That's it for topic 1.5, humans and pollution. If you find this video helpful, please give it a like, consider subscribing to my channel, and I'll be back soon with another ESS video.